Welcome back. It is time for our wrap up, but I'm not going to call it a wrap up today. Today, this is our launch session because these students are going to launch their rockets, right, Milton?
That's right, man. We're so excited. You all have been kicking butt and taking names today. So I want you to when it's time to show off your vehicles, all we want you to do is put your thumb up. Put your
I
thumb
think
up and
I
say
see
that you are
people with
ready to
signs.
go.
I saw a
Oh,
sign pop up already.
shit.
They're ready to go. Are you ready for
Oh,
this,
right.
Milton?
let's just jump right into it. Let's do it.
All right. I have DC Everest is the first one ready to roll. Check this out.
Oh, it's hard just getting a screenshot fast enough. Sheesh.
All right,
I'm
DC
loving the
Everest.
banner.
3, 2, 1, go.
Oh,
Oh man.
what do you call that, Milton?
That's a fail to launch, but you have another opportunity. You got to just rework this design for sure. It's a great design. Go back to the drawing board. We'll come back to you,
All
DC
right, we'll
Everest.
come right back. There was another group that was ready to go. Snow High School is ready. Their camera on. Snow High School, I'm going to spotlight you for everybody. There they are.
Hey, look at the microphone.
Oh.
Nice. That's professional, man. Oh, you don't have to put the mic down. Keep it going.
Oh, we're on
Oh,
the move.
he's the reporter. He's the reporter at the launch site at
I
Keynote.
get camera shy.
Nice.
Oh, look at
This
this.
is professional.
Is there going to be an official countdown?
Yeah, we need a countdown.
3.
Reworked it. Wait. They're still working it.
3, 2, 1.
Nice. Oh,
Wow.
excellent. Man. Oh, man, that was really good. Excellent. And they did that with just one straw. I was surprised. That was just one straw, Monica. I thought they needed two, but they knew better than me, for sure. Very nice.
They muted. I don't think they
Very
want to chat
nice.
with us.
Snow Hill, yeah. You don't want to talk about it?
Oh, Preston is ready. All right, Preston,
Okay,
you are up next. I'm going to spotlight you. Please
We
unmute
sure
and chat
are.
with us. Oh, we know that.
Hey.
Look at this.
Wow.
All right, what are we doing? They can hear you. Move. Can you move that desk? Move that desk.
Man, it's so cool to talk to you, Edgar, man. This is the man right here. Sheesh.
All right, you know me. All right, you ready? Can you hear
Look
me?
at all
Hi,
these
guys.
rockets. We
Hi,
can hear
everybody
you.
out there.
Uh-oh.
I need a little assistance.
Good job.
Oh,
Do we have another one that's ready?
We have another group. We have another group.
We have another group. All right.
So this one has scissors attached to it.
They attach scissors as a weight to try to get it
Let's
up.
see if it works.
Oh,
with the
wow.
scissors.
What? I've never seen that before, Mr.
Well,
Martinez.
they're trying to counter the weight. I'm letting them rock. Go ahead.
That is crazy. This is crazy.
Ready? And stand back.
Can you like? Okay. Okay. There you go.
There you go.
Hey, that's pretty good.
They just learn. Thank you, guys.
That's pretty good. Thanks.
Thank you. Great job, Preston.
Yes.
All right. If anybody else is ready to share, you can just put your thumbs up or your hands up in Zoom and we can spotlight you. If you are not ready, Milton, while we wait. Oh, Comac High School. Let me find them. Oh, there they are. There we go.
Mute. All right, we're unmuted.
We can hear you.
Okay, awesome. So our design, we are a bit unorthodox. We have no actual balloons that are bringing it up. We are using a slingshot instead.
Oh,
Oh,
man.
okay.
I love they thinking outside of the
Yes.
box.
Thank you. But
Ideation.
work, and we have video of it. Here, take this.
This is nice. Hey, it wasn't in the rules, so yeah, you gotta.
Yeah.
3, 2, 1. Like I said, it might take a few times.
No, that's just cool. That's crazy because there is a slingshot rocket out there that we have in our wrap up. So you are on it.
Awesome.
Behind them, that's ready too.
Yeah, Betsy said, good thinking on potential energy. That's right.
Take this.
Yeah, I'm listening to Aaron on the.
Okay. Here's your next attempt.
Very nice. Hey, that's actually good. That's good.
All right. I think
Thank you.
Nice. There it is. Excellent.
mission accomplished. All right. And there's
Yeah.
another group behind you. Are you guys gonna launch that one? Go ahead.
Yep, we're ready.
This is Comac High, the slingshot.
Triple booster here, Milton. Check this design
Yeah,
out.
that's nice. Slingshot. Comac is bringing it.
Yes. Oh.
That's all right. You still got to, oh.
Oh.
I mean, we
Hey.
got enough by the
Not bad. Hey, rework it. Maybe we'll come back to you.
All right. And does somebody else have their hand raised? Notre Dame Academy, are you guys ready? I saw that in the chat. Yes? All right. I'm going to spotlight you. Hi, everybody. Oh,
And they're ready to go.
they're ready.
They are ready to go.
Yeah.
Hey, be safe.
Ready? Ready? Go.
Oh.
Oh man. Oh, try it again. The rocket still works. Rework it. Maybe add 2 straws. Try it again. I love the energy.
Oh,
Great
I think we
energy.
have another group ready. Let's see this. Let's see the second style. Second launch here from Notre Dame. Success!
Nice. Very nice. Great job, Notre Dame.
Fantastic. Great job, Notre Dame.
Hey, does anyone want to talk about how they made that design? Any takers?
You want to come up and chat with us? They just want to launch for us.
Just-
They don't want to
just
talk to
one.
us.
No talking.
Let's see. Notre Dame, you want to chat with us? You can unmute.
Yeah, who wants to talk about the rocket? What was challenging? What was challenging about develop?
We
Go
put
ahead.
it all the
Great.
way down. The string was, we did one balloon and 2 straws. And Dr. Howell stood and held the clip, and Sienna held the string down, and I released the balloon and it went straight up.
Excellent. Was that your first design, or is that like your second or third iteration of that design?
Like third, fourth.
Oh, nice. So that's engineering right there. Great job, you all.
Thank you.
Thanks for chatting with us, ladies. Great job. All right. I don't think anybody else is ready to launch at the moment. Milton. I don't see
right.
any hands or anybody, so I think you're on until we get our next launch that's ready.
Okay, let's do this. Every time it's like as soon as I start sharing this presentation, someone puts the thumb up and says they're ready to go, right? Let me share my screen. You all have been doing a great job today. This is our, Monica renamed this. It was a wrap up. This is our launch session today. I gave you all just a little bit of my background of how I got involved with space vehicles. You can see Awesome One, which has been a challenge to develop, but we are almost there. This satellite is about 18 feet tall, and it's gonna blast off into space. What you're seeing here is our service and payload and some technicians developing it. It's not just engineers. We have scientists, we have finance people, we have technicians who also developing this rocket, which is awesome. And what Awesome does is it repairs satellites in space. Everything in engineering needs a problem. Like if you don't have a problem, then you don't have any design solution to implement. Everything needs a problem. This is why engineers, we love problems. We love problems. We're always thinking of like, what's the next problem? Because problems bring innovation. You all have been working on a lot of problems today, and seeing that slingshot design, there's been a lot of ideation and innovation, thinking outside the box and working in teams where there is a diversity of thought. Everybody's not thinking about the same thing. We're all thinking differently. So what you see in this picture is this orange satellite has ran out of fuel, and our satellite Awesome One is going to refuel it. It's going to cut it open and refuel it. Let's look at the real deal. Like, let me see. I'll show you the real deal as well. This is a test I showed earlier, and let me just speed this up a little bit, just showing the same thing you saw before. This is a 7 degree of freedom, the real robot arm grabbing onto a mock-up of that Landsat 7 satellite that's in space. You'll see it's going to push on the satellite and try to grab onto it to demonstrate some of the mechanics and dynamics that are going on. You had a lot of mechanics and dynamics to deal with your rocket as well. And this is showing us testing it on the ground before we launch it. Testing on the ground is so important before you launch, because once it's in space, we can't fix it, right? Unless it's OSAN 1. But I also want to highlight this. Testing on the ground is important. You see, this is our service-instant payload. And what we have here is we're running a very short vibration test on our service and payload. The reason that we're vibrating this spacecraft is because when it's placed on a rocket, the acoustic energy and the acceleration is so strong, it could break this entire structure. So we're trying to make sure that our payload is strong enough to survive all of the environments. That's mechanical, it's thermal, it's radiation, it's all of that great jazz. All right, that's what we're doing there. And what I wanted to talk about next is, if you can pull up Slido, I want to talk a little bit about your experience while we're waiting on some other folks to show off their rocket. I want to know what you enjoyed the most about this lab. So even if your rocket isn't done, if you can go to slido.com, that's SLIDO.com, and type in those numbers. So building and assembly, great. We got some building and some assembly. That's a great step in the engineering design process. It's a fun step. Design, yes, that's good. That's like the second step in the engineering design. Testing, right? What I love about testing is you can test and fail and test and fail. The more that you fail, the better innovations that you come up with. That's excellent as well. Working in teams. Hey, Monica, teamwork makes the dream work, right? I love how I have this design, she has this design, right? They have another design, and you come up with something that is either a compromise or maybe an innovation, something you never thought about, by combining your different diverse thoughts. Troubleshooting, that is really, really good. This is one thing in engineering and science and anything in life. Don't give up. If something fails, if there's a problem, you got to keep moving forward, right? That may be your homework. It could be college. It could be relationships, anything. You don't give up on the first try. You got to keep moving forward. That's perseverance. One of the key attributes you need in life to succeed is perseverance. Excellent. So building and assembly turns out to be the funnest, the most enjoyable. Hey, I'm not mad at you. I love building and assembly as well. Hey, we talked about some good stuff. How about some challenges? What was challenging? What was the most challenging aspect of this design? And if the answer isn't here, that's fine. You can type it in the chat. What was challenging? Thank you, Monica. That was perfect. It's like, are we reading each other's minds? What was challenging about it? Yeah, attaching the straw to the balloon. And since you brought that up, don't forget, if your rocket design is unstable, add another straw. I know you're thinking, man, that's going to add some complexity. It's going to add some friction. That's what engineers do. It's a trade-off, right? It may take me a little bit longer, but will I have a more successful design? Sure, maybe I will. It's a trade-off. Someone said their balloon exploded. That's why the logistics center sent you 9 balloons. That's right. You could do this 9 times and still get it to work. Yeah, setting up the launch system, the fishing line launch system. One, it has to remain stuck to the ceiling. That's tough in itself, but it has to be stable on the ground. It's got to be linear, straight up and down. That is really, really good. All right, getting the rocket to move straight, that's excellent. Releasing the rocket, that's great as well. attaching the straw to balloon. These are great. These are really, really good. We got a couple more folks coming in. Yes. All right. Anyone ready to show their rocket? Anyone? We got any takers?
Any
thumbs?
second launches?
Oh, yes. Thank you, Monica.
Plattsburgh, are you ready? I see the movement there. I'm not sure if they're ready.
Second or third time is a charm. When you all do show off your rockets, this is not only do we want to see this rocket, but we want to learn from you. Others want to learn from you. We want you to talk about what worked well, what didn't work so well. What were some challenges, right? How did it perform? And how can you improve the performance? That's really, really important. So Moore Catholic High School said, we learned a lot and it was very exciting. I feel the same way. Plattsburgh, New York says, we're working it. Let's do it. Oh no, that's Constance. Sorry. Thank you, Constance.
Milton, I just spotlighted this school design. They're not there, but check out this design. Can you see it?
Can you spotlight it one more time? Is
Sure.
that Archimedes?
Yes. Look at this.
That is really nice. It's
Look
nice.
at that.
Come on, man. You gotta, man, it's not spotlighting for me. Let me try. I gotta get a snippet of
I'm
this.
sorry. I'm
That is
sorry.
nice. Wow.
Great design.
You gotta launch that. You gotta show us. Does it work? Man,
Can you unmute and chat with us? Oh, here they come. They're gonna unmute. Is it spotlighted for you now?
Hello?
Hey
Yes,
there.
it is.
Hi.
Wow. That's
Can
a
you-
first.
So hold on, I have to turn off the other.
I'm gonna mute.
Oh.
I'm gonna mute.
Just so you know, after we speak with this teacher, we have another group that's ready. So Comet
Okay,
Academy
okay.
is ready. Once we get this Archimedes, I want to hear about this design.
Definitely. Archimedes Academy. Man, this is a never seen before. I've never seen anything like this.
You guys
This is the
hear me?
first. Oh, that audio. All right, we'll go to Comet Academy and then we'll come back. Okay. Let's go to Comet Academy and spotlight.
We are ready. We have our first group ready. So they are up
Fantastic.
at the front and it's starting down. If you guys can see, they went ahead and did floor to ceiling. They're very confident that they need more space than that. So
Okay.
All right,
Okay.
let's see it.
Could you do a countdown? Because we want to grab a
You guys wanna
snippet.
do a
Do a
countdown?
countdown, please.
okay, we'll do a countdown. 10, 9, 8,
Ooh, I love it.
6, 5, 4, 3, 2, 1.
Oh man. It was such anticipation. I mean, that's all right. Work it again, man. We were really anticipating this, man. Hey, put it back together. It's all good. Yeah, the sound effects are awesome. You're
All
right,
right, they're
Shannon.
gonna troubleshoot
One more
that.
time. One more time.
One more time.
No, I mean we'll come back to you
Come
one more
back.
time.
All
We can go
right.
to another group.
Archimedes. Let's see if they got their audio worked out. Let's see.
Hey Archimedes, that rocket is just twirling
Yes.
in the air.
Can you hear me, guys?
We can
Yes,
hear
we
you. Thank
can.
you.
Awesome. So our design is a little bit different than other people. We did design like the base for this, for our spaceship, and then we added propellers on each side. So we do expect that this one is gonna be elevated, lifted up, and as it's passing through the thermosphere, these propellers are gonna be burn out, and the space shuttle is gonna go up.
So realistic.
So that's our design. Unfortunately,
Can you turn it around? Can we see the other side?
I can't really show you how it's taking off, but we are in progress.
Can you turn it
Can you show
around?
us
I
the
want
other
to see the other side. Yeah. The other side.
Turn it
Excuse me?
around. Can we turn it around?
Sure.
Yes.
Yeah.
Awesome.
Very cool. Sheesh. Can't wait to see that launch. You got to take a video of that launch when it's time, and please share that with us.
Thank you so much. That was awesome.
Bye now.
All right. I don't think we have another group that's ready just yet. So Milton,
I have one group that is almost ready, but they want to show you guys the design before they connect it to the string.
Let's do it.
So is that okay?
Of course.
Yeah, that's excellent.
All right. Yes.
Ooh.
All right.
Okay.
Tell them about it, Dr. Cecilia.
Coming in
This is our
strong.
design. His name is Bob. We put
His
on the
name
side.
is Bob.
And then we have two little things right there to hold it up. Yeah.
Oh, so you have like a stand for it, like a support on the bottom. Oh, nice.
This is
Very nice.
these are some intricate designs today, Milton.
Yes, they are. I mean, you can tell they put in the work, you know.
Yes.
They took
Are,
this
are they going to set it up to
serious.
launch right now?
Yes, they are. They just wanted to show you guys real quick. So
All right,
I'll let you know when they're
fantastic.
ready.
I'm glad they
They
did because
just
then we
wanted
wouldn't
everyone to
see it
meet
behind
Bob.
the table.
This is the perfect school that says Comet Academy. I just picked that.
It is perfect. We are the Comets. That's our mascot. So I didn't even think
Nice.
about that.
This is perfect.
All right,
Okay.
Comet Academy is setting up Bob for his launch. Hopefully it's a successful launch for Bob.
Same here. I hope it's successful. And while we're waiting, like, hey, we do want to talk about next steps just a little bit, right? You know, you all are in high school. That's where you started. Hey, that's where I started as well. But you don't have to be a scientist. You don't even have to be an engineer right now to get involved. You can get involved as a high school student. We're going to talk about internships on the next slide. Get paid to do what you do, right? But there's some manual operations, even from high school. If you have a certification, there are things you can do, even at NASA. If you pick up a 2-year degree, an associate's degree, maybe at a community college, we have technicians that work at NASA. It's not me, the engineer, it's not me, the manager that's putting the spacecraft together, that's hooking up the wires, that's placing the instrument on the spacecraft, that's vibrating it. No, that is our technicians, our operations folks that are commanding the spacecraft in orbit, right? And it's a great degree, shorter amount of time. They still get paid really, really well. You wouldn't even know the difference. But if you really want to specialize, like I want to go in aerospace, I want to specialize. Maybe you want to specialize on propulsion or orbital dynamics. You want to design the mission or structures or aerodynamics, all of that stuff. Hey, maybe you want to pursue a 4-year degree. And after you pursue that 4-year degree, if you want to take it a step further and do some research, you may go at graduate school or a PhD. Or maybe like me, I'm a project manager. I went back and got my master's in project management and in robotics because I wanted to lead Awesome One, which is managing a robotic mission, right? So there are a lot of opportunities for you. I also want to highlight that one way to help you navigate this whole process is to get involved with organizations. Now, you're already down with Engineering Tomorrow for life, right? You're already down with us. But other organizations like the National Society of Black Engineers and Women Engineers and AIAA Aerospace, that's how you get the word out. Like only the thousands of us right now that are on this line got a chance to see your awesome rocket. But if you want to get an even farther reach and build your reputation, get involved with organizations. And it seems like, Monica, there's a team that has raised their hand.
Comet Academy is ready to launch.
Let's do it.
There they are. Bob is ready for launch.
Don't forget the countdown. Don't forget the countdown and take it slow.
Oh, they're on mute. Comet Academy, can you unmute?
Yes, sorry about that. I think that we just lost our string, so they're having to fix it again.
Oh, okay.
Are y'all ready? Okay, I think they're ready.
All right.
Trying to move our tables for everyone.
Hey, there's still two rockets left. There's still 2 left. I can see it.
Hang on, let me turn my volume up just a little bit.
Maybe not. Maybe.
Poor Bob.
Maybe not.
Would you mind saying that again so they can hear this time?
Oh, we were saying maybe they could use those last 2 rocket balloons that they have to still launch it. I know one of them deflated, but it seems like there's 2 that are still working. Can they launch with just those 2?
So since you still have 2 working balloons, he's thinking that maybe you can use that last one or one of the ones that's still there.
If you remove the cups, maybe you remove the cups.
Okay, listen, guys.
Oh, okay, there we work. Hey, we'll come back to you all. DC Everest has their hand up as well. You all are doing a great job, Comet Academy.
DC Everest, I'm gonna spotlight you for everybody. And here we go.
3, 2, 1.
I like the setup. I like it. I like the setup. I do. Pittsburgh is ready. Everyone's ready to launch now,
Everybody's ready to
Monica.
launch.
Everybody's
Yes.
ready. That's all right. Take your time, DC Everest.
All right. We're coming back to DC Everest.
Yeah, we'll come back. It looks great.
Okay. I'm going to go to Plattsburgh. They are ready.
Hello, we're Plattsburgh. We got a launch ready. It's a little far away from you.
We can see it.
Okay. I'll count down when I say go. 3, 2, 1, go.
Ooh, man, it's been a tough day at the launch site, Monica. It's been a tough day. You all, hey, we thank you for trying, and don't forget, before you jump on, before you raise your hand, you can always do a quick test as well. Nothing wrong with a quick test, quick booster test. Release a little air and see if it's rocking and rolling.
I think everybody's still working their launch sites to get them ready. I don't think we have anybody ready to launch right now.
Okay, that gives me a perfect opportunity to pick up where I left off. We talked about getting involved with some organizations like Engineering Tomorrow, which is great. We also wanted to say, with the skills that you have learned today, you should be applying to internships right now. You know, you should be applying to internships. Great places like NASA and Blue Origin and ULA and SpaceX, right? Are all developing different types of vehicles that go in space, different types of missions. And you've worked on a team today. You've troubleshooted, you've designed, you've endured and persevered multiple failures and launches. That's all we want. We want somebody that's willing to try and keep trying. We want someone that's willing to persevere through obstacles. That's exactly what we want with our teams today. So you should be applying to internships, and these organizations that you're involved with, they can help with that. And finally, you're probably thinking, hey, well, how do I apply? What do I do? Well, with the skills that you've learned, you should apply some of these skills and place them directly in your resume, directly in your cover letter. Design optimization. We had a team that said they worked on 4 rockets before they got one to launch. That is optimizing a design. Vehicle mechanics. You learned about mechanics. You learned about system integration. You had to integrate the balloons. You had to integrate the launch system with the fishing line. You had to integrate the tape, the payloads with the multiple paper clips. You had to integrate your fins, some like those huge wings and fins that are applied to that rocket. You learned some integration. You learned about the center of gravity, right? You need the rocket to be balanced. You can't have a lot of weight on the left side, or else it won't fly, right? So you had to balance those forces and distribute it. And you've even learned, as you complete the lab, you'll learn some about data analysis as well. So you all have done a great job today, kicking butt and taking names. Before we transition, is there one more team that wants to highlight before we transition to our
DC
next?
Everest has their written sign ready to go. All right.
Cool.
I'm going to spotlight DC Everest. Thumbs up. You can unmute if you'd like.
Do you see DC Everest?
Yep.
More Catholics said they have a video to show as well.
And I have a hand up at Maria Regina if you'd like to go see Maria Regina. Thank you, DC Everest. Maria Regina. You guys can unmute so we can hear you. Oh, look at this. They got four balloons there.
Okay, cool.
Yeah.
4 balloons.
Yeah.
Hopefully they ran a little test ahead of time. Yeah, I hope so. We'll see. The tension. It's a lot of rockets, Monica.
Yes.
That's a lot of balloons.
1,
Okay, well, you can rework it. It's the balance. It's the balance. You want great job, Maria Regina. Great job.
Great
job.
All
right.
right.
Maybe the last one, the video.
More
the video.
Catholic.
Good job.
Let's see if we can get them to share a video. Hey there. Oh, you're not ready? Sorry. You ready? All
Okay.
right, let's see. Ooh.
Nice.
Oh.
Oh, wow. That was awesome.
Please
Jeez, a
share
lot
that
of great.
video with us. Tell your teacher to email that to us.
Yeah, that's a good one.
Oh, they turned off the
That's a
camera.
good
They
one.
didn't want to
That's a
be on
good one.
screen. All right. Thank you, more Catholic. All right.
All right. Are we ready?
I think so.
Good deal. Well, you all did a great job again. Let me just try to share my screen. This is our time where you have an opportunity to speak to hear from and speak to an outstanding speaker. Before we do that, I just want to share something. I want to give a big shout out to Ethan and Annie and Brianna and Morgan and the hostess with the mostest, Monica, and the entire ET team, the engineers that worked the breakout sessions, the other mentors that were here. You all absolutely killed it. It was truly out of this world. I'm just throwing in a couple screenshots of Annie and Ethan doing their great work in business there. But as Monica would say, you all were the stars of the show. So Archimedes Academy, look at that bad boy. Man, that's awesome. Comet Academy, perfect name for a rocket. Mr. Edgar Martinez and your team, Comic and the Slingshot. Look, the Slingshot design, that is so crazy. And every single team that showed up and showed out today, we appreciate you and we want to see you at our next lab. So what we're going to do today is we have an outstanding guest speaker for you. I mean, I'm excited about this because, man, I want to be an astronaut, and this person has actually achieved it here. Miss Marcia Ivines is an astronaut, an aerospace engineer, a biomedical engineer as well. She received a bachelor's from Colorado University. She actually was a flight test engineer on the shuttle training aircraft before she became an astronaut. This is unbelievable. 5 space flights. I mean, space is literally her second home. 1,318 hours in space. I'm not highlighting this, but did you know that she has made it to the Astronaut Hall of Fame? Unbelievable. And even now, she is the director of the Human Systems Integration. She's director of that company, and Betsy knows a lot about that. Could we give a huge round of applause for an outstanding astronaut that has given their time to us today? Let's give it up for Marcia. Thank you so much for being here.
Thank you, Milton.
Sharing.
Thank you. And it was fun to watch your rockets. I mean, that was actually very cool. Let me share my screen here and okay. So can you see a big old Earth?
Yes, we can.
Okay. All right. So what I'm going to talk to you about today is the history of human spaceflight. And I show you this picture just to preface it by saying that every picture that I'm going to show you was taken by a real human being. So that's important to note, and especially this one. And we'll get to where that one was taken. So the story starts in 1959. No one had ever been to space yet, and the Soviet Union and the United States were in a race to see who could actually put somebody in space and then send them to the moon. And the Soviet Union won the first part of that race by putting this guy, Yuri Gagarin, into space. In the United States, we were starting to build this little capsule, and you can see the people there for scale. And we were literally going to stick this on a ballistic missile and send a human person into very high altitudes and try to get him eventually into orbit. And in the run up to do this, there were some literally spectacular rocket failures. So anything that you saw in your balloons today that has failed, trust me, we have been through this with real live hardware before. The first 7 astronauts that were selected to fly were these guys. They were all fighter pilots, military fighter pilots. Well, actually, this was the first guy that was selected to fly, and he was the first one to actually fly in that capsule. And afterwards, then we put Alan Shepard in that. And you can see it doesn't look very much different than the way the monkey was strapped into his seat right there. We had 2 flights that didn't quite make it to orbit, which was intended. And then we sent John Glenn on a little bit bigger rocket to be the first American to orbit the Earth. It's a real picture of John Glenn from space, orbited the Earth once and came back and landed. And when he landed, as all these capsules did, they land in the water. And then you can see the helicopter picks the astronaut up to bring him back to shore.
That's so cool.
So we had 7 of those flights. And then the next program was called Gemini. It was a little bigger rocket, a little bigger capsule, and it taught us to do a couple of things. One was how to fly 2 spacecraft together going at 17,500 miles per hour, which is how fast you go around the Earth. And that's formation flying, really taken to a big extreme. And then the other was how to do a spacewalk. So spacewalking was going to become important, particularly when we got to the moon, and it's in a vacuum, even though you have a little bit of gravity, but doing it in Earth orbit here was the first step. And this was really hard to learn. There's vacuum in space, so no air and no gravity. And all of the air and all of the pressure that keeps him alive is in that suit run through this umbilical line that is connected to the spacecraft. So maneuvering around out there was actually really hard to do. This is how much room there was in that Gemini capsule. And imagine the longest Gemini flight was 14 days. So think about living like that for 14 days. In 1968, in the Christmas of 1968, we launched the Saturn V rocket after a number of test flights and some interesting failures. But we finally launched one, and we put a crew on it. And this is what it looked like inside the Apollo capsule. So you see not very much room, not much more than we had in those other little capsules, but we sent that crew around the moon. And this was the first time, this was December of 1968, and it was the first time anybody had been able to look back at the Earth from not being on it and see the whole Earth in its entirety. And that was incredible. This was Apollo's Christmas present to the world in 1968. In 1969, we sent the first crew to land on the moon. This was in Apollo 11. So the way that worked is the Apollo capsule had a lander that was connected to it. The capsule stayed in orbit around the moon with 1 crew member in it. And then the lander went to the surface of the moon with the 2 other crew members. And, you know, the moon is sort of an inhospitable place. This is a picture taken from one of the landers prior to landing. This is what the lander looked like. And this top part of it here is where the crew stood. They didn't even have any seats. This is how big it is. And so this was the engine down here that they landed here is for scale on the outside. And then it serves as the launch platform for the top part that will go back and re-rendezvous with the Apollo capsule. That first landing on Apollo 11, they spent 21 hours total on the surface. And that was it. They went maybe a kilometer wandering around, but that changed the game for everybody since we had landed on the moon. We had 5 additional flights. They allowed the crew to go farther. We had a rover, like a little dune buggy that would allow you to drive around a little farther and collect other samples. And we spent a lot of time doing just that, collecting samples. And you can see the guy up here in the upper right-hand corner, he looks fairly clean, except look at his legs. And then look at the other 2 crew members. They spent about as much time in the soil as they did collecting it, because those suits were really, really hard to maneuver around in. And even once they took the suit off, they were still covered with lunar regolith. And regolith is not just dirt, it's like little shards of glass. It's pretty nasty stuff. So learned a lot on those flights. The Apollo capsule also landed under parachutes and then is recovered again. And you can see how burned these capsules look from coming back through the atmosphere. They're all used one single time. We had 6 flights. The last one to the moon was in 1972, and no one has sent people back to the moon since. But we still had hardware left over. The Apollo program was canceled for political reasons, not for technical reasons. But we had Apollo hardware left. And so the United States actually had a space station before the International Space Station, and it was called Skylab. And it was based on a fuel tank from the Saturn V rocket. And we had 3 crews that spent between 29, 59, and 89 days on board. And it was a huge volume on the inside. I mean, lots of room for them to be in. That was in 1973 and 1974. In 1975, we actually joined a Apollo spacecraft with 3 crew members. They're the ones on the left, with a Soviet Soyuz with 2 crew members. And so this was called the Apollo Soyuz mission. And we had a true handshake between the Soviet Union and the United States in space. The Russians actually never made it all the way to the moon with their rocket, but they've been flying successfully in space ever since, and they fly this rocket here and the Soyuz capsule, and this is the way they fly today, and we've been flying American astronauts on that capsule too. The crew is in the center part here where the window is. They've got a cargo module on the side, on the top, and then their solar array and their engine, and the center part is the only part that comes back. This is what it looks like inside the Soyuz. This is not very much different than the way it looks inside all those capsules. And this is a Soyuz landing. This one was about 1.5 years ago. This is a normal Soyuz landing, nice landing, walk away from, crew gets to say, hi, had a good day. And this is the way their Soyuz capsule looks when it comes back from Earth. So again, that is not reused. This is how the crew is recovered. As an American and 2 Russians in that crew here after this was last winter. Actually, this was during COVID. So this is recovering a crew in the days of COVID. In 1981, we started to fly the space shuttle, and in the mid-70s is when we began designing it. And this was the world's first reusable spacecraft. The shuttle orbiter is this vehicle here you see. It looked very much like one of your balloon designs today. And this was reusable, and it had a tile material on it that would not burn. It would reject the heat so that you could use it again. It had 3 main engines that were fueled by liquid hydrogen and oxygen that was in this big orange tank, and that's the part that was not reused. And then 2 solid rocket motors on either side of it, and those had a solid propellant, and then those were reused again. So we reused this rocket. The shuttle was designed to fly like any capsule in space, and then come back and land on a runway with no engines. So those engines were only used for the first 8.5 minutes. So this was a 200-ton glider that came back to land again. And it was going to do all sorts of miraculous things. It was going to fly everybody's payload. It was going to fly every 10 days. But the biggest it was going to do is it was going to fly girls. And so this is the first time that women had been selected into the astronaut program. So those were the first 6 that were selected in 1978. You think being an astronaut is a fairly glamorous job, but I remind you, this is the last view anybody sees of you before you get in the vehicle. This is what it looked like in the shuttle. This is me in the foreground here with the glasses on. So we had a whole lot more room because we lived in here for up to 18 days at times. In the shuttle, the crew is in this front part where the windows are, and that is all pressurized. But in the back, it was 60 feet long and 15 feet in diameter, and we could carry all sorts of things to space in there. We carried a number of satellites. Some were kind of slingshot out of the cargo bay. Some were picked up with the robot arm. There were communication satellites and experiment satellites, but the one that most people remember is the Hubble telescope, which was designed to be launched in the cargo bay, then picked up with the robot arm, put into space, and then over the years, the shuttle would come back, fly right up next to it, grab it with the arm, put it back in the cargo bay, and repair it. For the last 10 years of its life, in the last 37 missions, we used that shuttle to assemble the International Space Station, one piece at a time. So the biggest piece on the space station is as big as the cargo bay could be. So this was the first piece, which is a node, which is kind of like the center point of a Tinker toy. So I can attach something at both radial ends and well, 4 radial ends, and then at the top and the bottom of it. And so we took that module and we stuck it on the first Russian module that had been launched. And then we put on another Russian module, and we put on a solar array. And at the end of the year 2000, we sent the first crew to live on the International Space Station. And since that time, there have been 70 different increments, and somebody has always been in residence on the space station. We added additional modules to it over the years. This is the first laboratory module. I actually put that on myself. We added a robot arm. We added additional modules. We added more solar arrays. We started bringing modules from the European and the Japanese Space Agency. We added a big truss so that we could put additional arrays on. And then this is a real picture that shows the shuttle actually docked to the space station. Real picture taken by a Soyuz that backed away and took that picture just to show you what it is for scale. And so here is the space station as it lives today. So here's what it's like to be in space without any gravity. And here's how that picture was taken. That's me. A little bit more hair then at the time. And the cool thing about having no gravity is that there is no up. Each one of these guys thinks that they are up. Without any gravity, you can lift very heavy weights very easily, and you can do some interesting things with your body that you cannot do here with gravity on Earth. But the coolest thing is that you can't walk, you have to fly. And so here it is flying. And you notice you never see them stop, because stopping when you're flying like that means you crash into something. When you get experienced, here is the way that you move through space. Watch his feet. Now, he spent a year in space, so he got really good at it. But you can do some interesting things with your body in the absence of gravity. That's me back there taking a picture. We ask you, please don't try this at home. And there's some interesting physics experiments you can do in space. So, you know, for every force, there is an equal and opposite force. So imagine if you are hit with a heavy object. Now here's me, and I'm not moving forward or aft, but just by wiggling my hips around, I can turn a complete 360 degrees. Here's a demonstration of the ice skater. This is conservation of angular momentum. As he raises his arms, he will slow down. And when he closes his arms, he speeds up again. And without any gravity, you can spin all day long and you never get dizzy. And nothing will ever stop you until you stop yourself. Here's another one that you can do in space. It's kind of cool. Now he's trying to do that same thing that I did with my hips, but guys can't sort of get that hip action going. You've seen people floating around, but let's say you want to not float. And it doesn't take much to make you float. If I touch the key on a keyboard, I would immediately float away from it. Sort of like Milton showed in that experiment where the robot arm touched something and it pushed it away. So in order to not float, all over the space station, you hook your toes into something. Here are 2 toe straps, and you can do that when you need to make very precise motions with both of your hands. The guy here on the left is doing a robotic operation. But you don't always need a foot strap. You could just loop your toe around something if you needed to stay in one position. This is a ball of water. And in the absence of gravity, surface tension is the strongest force there, and it holds the ball of water together. This is a ball of orange juice, which is much more photogenic. The way you drink is not by releasing a blob of liquid like that, but you actually take a bag that has a powder in it that says orange juice. So it has a liquid or a powdered orange juice in it, and you fill it up through a water dispenser, and then you have a bag of whatever that drink is. We have no oven and we have no refrigerator, so the food is already cooked. And then it's been freeze-dried and vacuum packed or thermostabilized so that you don't have to cook it real time. In the freeze-dried version, they come in these little packages like that. Tells you what the food is, how much water to add. You add water from the water dispenser, whether it's hot or ambient water, and then you put it in an oven that just heats it up a little bit. And you don't get a plate, a knife, or a fork. You get a spoon, and then you cut the top off of the package, and you can put your spoon in that package and eat what you need to eat. You can see in the back, there's all these little plastic bottles of things, and that's the liquid condiments, liquid salt and liquid pepper. You want your food to not have a lot of crumbs, and so here's a pretty good space food, honey and peanut butter. Here is a piece of meat. The meat has already been cooked. Then it's been thermostabilized and put in this package, and you eat it like one of those push-up popsicle kind of things. You cut the top off, roll up the bottom, and then you can hold it and chew on the meat. And then there's tortillas. And so we put lots of things on tortillas because bread won't stay fresh. Here is a crew making pizza. So they've taken a tortilla. They have some stuff in squeeze tubes like tomato paste and tomato sauce. And they've got sliced pepperoni, it looks like, and cheese. And they've made themselves a pizza. The crew will spend 3 or 6 or 8 months or 12 months in space, and they don't have the option to go to the store and get fresh food. And so every 3 or 4 months, a cargo vehicle arrives at shuttle with new supplies, the things that they need. And we always send fresh food, fresh fruit and vegetables to the crew. They're always very thrilled about that. And now when you get creative with your tortilla, you've got fresh vegetables and things to put on it. Here's how you would eat your M&Ms in space. And here's the high-tech NASA trash compactor. Nobody collects the trash in space, and so we collect the trash. We put it in a bag. We are our own trash compactor. You put all of your trash in bags, and then you put those bags in other bags, and you wait for the cargo vehicle to arrive. You offload the good cargo, and then you fill it up with all of the things that you want to send back as trash. And if you have a vehicle where you can send things back that are not trash, you package them up just like this. But if we want to trash it, that's the way it looks. Exercise is important. The crew on board the space station exercises 2 hours every day. One way to do it is on this bicycle ergometer. They're wearing shoes. You can see everybody's shoes here are clipped to a rail. And they're clipped into those pedals, and then you can dial a resistance in that box and pedal against it. The guy here on the right side, he's actually watching a movie while he bicycles. We have a treadmill that's bolted to the floor. You turn it on, the treadmill moves, and she's wearing a harness that bungees herself down onto the treadmill so that she can run. And then we have this device, and the sound you hear is actually the sound of it. This is a resistive exercise device. And it's moving because it is stabilized so that it does not impart any loads into the space station when he is doing these exercises. And you can do any exercise that you can do, resistive exercise, in a gym. Here is a soccer game. There's a crew having an international soccer game here, which is some interesting moves. See somebody running on the treadmill. That's a goal you wish you could see in real live soccer play. And this one too. Here's a crew having movie night. So they have a fabric screen they've stretched up across the wall, and they're watching a movie. And they get first run movies now that are uplinked to them. Here's how you take a bath. Remember the ball of water? Well, you put the ball of water on you. And so you wash a body part at a time. You put a ball of water on, you take a washcloth with some soap, you soap that body part, you put on another ball of water, spread it around, take a towel and wipe it off, and you do one body part at a time. And that's the way you take your bath. Shaving is normal. We have electric razors and straight razors. And some crew want to have a haircut. I mean, if you're 5 months or so in space, the guys in particular want a haircut. And so you haircut by using a device connected to a vacuum cleaner that literally sucks the hair in when you cut it. Not everybody, of course, cuts their hair. Here's how you brush your teeth. You have a toothbrush and toothpaste. You brush your teeth, but there's no place to spit, so you have to swallow the toothpaste. And here's how you would sleep. On the shuttle, we took our sleeping bag and you stretched it off to the wall, the floor, the ceiling, wherever you want to sleep that night, and you get in, and then you zip it up, and you take the blue straps here, which are Velcro, and you tighten it. Makes you feel like you're tucked in, and whatever you don't tuck in, like your arms, will float. Now, because there's no gravity, the blood doesn't all rush away from your hands, and they don't fall asleep. They just kind of freaky hang out there in space. So those of us that don't like that, you just tuck them in underneath the bag with you. You put your head on the pillow, which is a block of foam, and you Velcro your face to it. Now, if you think about that, it sounds a little strange, but when you go to sleep at night and you rest your head on the pillow, your neck is at rest. And if your neck is at rest, then the rest of you can rest. On board space station, everybody has their own little compartment to sleep in. She's got a sleeping bag and her drink bags, and her laptop is in there, and all her private stuff. And now, because we can have so many people on board space station, we have additional sleep compartments. And so this is the way you can sleep 4 crew members together. Each has their own private compartment. Here is the toilet. And this is the way, I'll tell you the way this works. This is a Russian system. For liquid collection, you slide your toes underneath of those straps, and you take this hose down and you connect it to the liquid part of your body. And when you turn it on, it's got a little suction in it that will then, as you let go, it will suck that liquid down into a tank behind the wall where it is processed back into drinking water. Or as the crew says, making tomorrow's coffee out of today's coffee. For solid waste collection, you open the lid here, you put a bag inside of this, and you close the lid, sort of like a diaper genie. You slide your toes in those straps in the other direction, and you hold on to the seat, and you do what you're going to do. And then there are dry wipes and wet wipes and things that are Velcroed in packages off to the walls. You clean all that up, put it in the bag, close the bag, and put in a new bag for the next person. And when that can, that silver can is full of bags, you cap it off, remove the can, put in a new can, and wait for the cargo vehicle so that you can trash it. We are the maintenance people on board, and so all tools have their space in a rack, in a locker, in a tray. They all have little pieces of Velcro on them, and in fact, the walls have Velcro on them, and even the clothing has Velcro on them so that things don't float away. Here is your desk, pens and pencils and tapes and scissors and small tools and things like that. Experiments on board, a number of experiments are done. We have glove boxes, a number of glove boxes for doing things with small things that you don't want to get away, or biological experiments. And one of the experiments the crew likes the best is called Veggie. It grows things in space. And so the crew always gets to sample what they've grown. This one was hatch chilies. And so then the tortillas got really creative with your hatch chilies. And then, of course, we are the experiment. Understanding how the body performs in the absence of gravity is important, so that we can understand how to prepare for crew members spending a really long duration in space. And finally, we get to do the maintenance on the outside of the vehicle, and we get to do spacewalks. This is actually 2 women doing a spacewalk here. Now, when we do a spacewalk, unlike the Gemini picture that I showed you, there's no big umbilical that connects you to your lifeline, to your air and your pressure. That's all in the suit with you, but you are always connected with a safety tether. And because we knew people would be walking all over the outside of this vehicle, we have these handrails all over the vehicle so that you can move yourself by going hand over hand all the way to anywhere that you want on the space station structure, all the way even out to the end. You can see they both have a safety tether connected there. On the end of the robot arm, we can put a platform where you can attach your feet to the platform, and then you can carry a large object someplace and do an installation if you want while your feet are restrained. And everybody is wearing a little backpack attachment on the back here. So should you come loose from that platform, or should your safety tether break, or you have to do a rescue, it's a little jetpack that will allow you to fly back to the structure so that you can hold on. Everybody takes selfies. So here is a spacewalking crew member taking a selfie. You see his arms are out, and you can see the reflection of the camera wearing a little spacesuit in his visor. The coolest module that we have on board Space Station is this one called the Cupola. It's got 7 windows in it, and it is a great place to hang out and watch the world go by. It's a great place to take a selfie. And here is what the world looks like as it goes by. We are at 250 miles above the Earth, not very far. In order to see that first picture that I showed you of the whole Earth, you have to be all the way at the moon. That's 250,000 miles away. This is the slice of Earth that we see from our orbit on Space Station. And there's some pretty cool things that you can see. This is a glacier in Alaska. Here is a glacier in the Himalayas. This is ice off the northeast part of Russia. This is the Andes in Argentina. These are mountains in Bolivia. This is the Namibian desert in the west part of Africa. This is the Sahara Desert in Libya and the Australian desert. And so, you know, it looks like no one could be living on this planet when you look at pictures like this. Here is a recognizable, probably the most recognizable landmass when you see it, which is Italy. And again, where are the people? Well, when you look at it at night, there are the people. So I have a lot of night pictures in here because I think they're very cool, but they're very descriptive also. And in all of them, you will see this little green line across the top here. That is the top of the atmosphere. And so all the air that we breathe is below that line. And we are only flying just slightly above that line. So not very far into space. Another recognizable landmass here. This is Florida. Here is Florida at night. It's turned 90 degrees here. Here's Atlanta right there. Here's Florida again, and this is the waters of the Caribbean, and really no body of water on the planet looks quite like this. Since I didn't know where you were all from, those of you that are watching this, I just started on the west part of the United States, and I'm moving east. So here are the Hawaiian Islands. Here is the coast of California. We're starting down here at San Diego. Here is Los Angeles. And up here is the Bay Area with San Francisco. Here is the Pacific Ocean. Here is the Sierra Nevada mountains. And these are the Rocky Mountains right here. This is the Grand Canyon. Here we are down in my neighborhood in Texas. So this is Dallas, Houston, New Orleans, Austin, and San Antonio. And all these little orange lights that you see here in the bottom, those are oil fields. Here are the Great Lakes. And here's a night shot of Chicago. Here is the Chesapeake, there are the Great Lakes. Here, the Chesapeake Bay area, moving up into Long Island and Cape Cod, and up into Maine and then Canada. Here is New York. This is Central Park here, this rectangle in the center, and here's Manhattan, downtown Manhattan. And they call it the city that never sleeps for a reason. And here is that same Central Park downtown area. This is Washington, D.C. And now we're moving into Europe. And so here is Dublin in Ireland, and here's Liverpool and London and Brussels and Paris. This is Tokyo. And here is Bangkok right here. And I show you this because all those green lights are fishing boats. Here is the Nile Delta here and Cairo. And here are, with a long lens in the camera, are shadows from the pyramids. And here is the Nile at night. We go around the Earth once every 90 minutes, and every astronaut who has ever flown has come back and said the same thing. You do not see the borders and the boundaries that separate the countries from space. There are no natural borders and boundaries. Sadly, there are man-made borders and boundaries. This orange light that you see line is the lighted border between India and Pakistan. This is the Korean Peninsula, North and South Korea, here, that piece of land that looks very, very normal. And here it is at night. This is South Korea and Seoul, and here is North Korea, and that's Pyongyang right there. Man-made borders. And then we see the footprint that we have put on the planet. This I show you, this is New Orleans here, and this is the Mississippi Delta. This is what it looks like normally. And I show you this so that you can recognize this pattern. In 2010, there was a giant BP oil spill. And so here you can see that same Mississippi River Delta, and this dark smudge here, that was the oil spill. Underneath of all of this smog somewhere is Beijing. And then we see natural phenomenon. This is a hurricane. This is what a thunderstorm, thundercloud looks like from above. And here, these white flashing lights that you see, those are all lightning strikes. This is moving across the Earth a little faster than normal. Like I said, we go around the Earth in 90 minutes. And so for 45 minutes, we see daylight. And for 45 minutes, we see darkness. So 16 times a day, we see the sunrise and we see the sunset. And because we are flying at a very high inclination, we see the northern and the southern lights from above, the aurora. So this is the space station as it exists today. And this is the crew. These 4 blue guys just arrived, and 4 of the red guys actually came home yesterday, I think. So they're down to 7, but this, I don't have a picture of all of them yet, but that was the crew. The Chinese have a very aggressive and a very strong space program. They have a space station, looks very much like the one I just showed you. They've been doing spacewalks, they've been doing assemblies, and they have gone to the moon. I mean, not with people yet, but they're getting ready to. Today, we are flying commercial space, and this is how we get Americans to orbit right now on this Dragon capsule. This is the crew, those 4 blue guys that I showed you. This was them before they launched, and this was their launch. And here we can dock Dragon capsule and a cargo capsule at the same time to space station. This is the way those capsules are recovered. They fall back into the water. They are reused. It's an ablative material, but it's put back on again, and they reuse that capsule again. The crew is not picked up from the capsule until the capsule is brought onto a ship, and then the crew is taken out. Boeing has a contract with NASA to provide crew access to space, and they're using this vehicle called Starliner. They have flown it without crew first. And so this is a real picture of the Starliner just prior to docking. They flew an instrumented dummy on board. That was their crew member. And when they come back and land, they land on the land under airbags like that. The next plan here in the United States and for everybody else is to go back to the moon. Like I said, we haven't sent people to the moon since 1972, but we have been sending rovers to land on the moon, a lot of them unsuccessful, but some of them recently very successful. So this is the Chinese lander. They have actually returned a sample from the moon. Here's one from India. Here's one from Japan, which fell over, but still worked. And last week or week before, we sent this one from Intuitive Machines in the United States, landed successfully on the moon. It also tipped over, but it landed successfully on the moon. But before we can land people on the moon, we've got to do a couple other things. And so we're going to launch the crew on this big rocket in its own capsule called Orion. And we actually flew this Orion capsule with nobody in it on that big rocket, and we flew it like an Apollo 8 around the moon. So here is a picture of that capsule between the Earth and the moon, and it landed successfully. And so now we've demonstrated that we can put people in that capsule, but we need a way to actually land people on the moon. There's the capsule recovery. And before we do that, the way we're going to do that is, this is the only non-real picture in the stack here. We're going to build a space station that's 5,000 miles away from the moon. And then we're going to dock the Orion capsule to it. And then we're going to dock that lander to the capsule and land it on the moon. And so that lander is this one. So this is, they actually flew this morning. This is before its second flight, but this is the Starship that SpaceX is building. And so this is twice as big as a Saturn V rocket. And the part that's going to land on the moon would be this one right here. And this was from this morning. They actually successfully launched this. They got it into space. They got it separated. They got the stage back. And then this part here, they lost contact with it as it came back through the atmosphere again, but a very successful flight for SpaceX. But the plan is that this part here will dock with that Orion capsule, and then the crew will get into this, and this is the part that will land on the moon. Right now, the plan is to learn how to do this, to go to the moon and do it successfully so that we can actually take people and go to Mars. Mars is about as far as we can go in today's current technology. This is a real picture of Mars taken from satellites. We have actually landed some rovers on Mars, but they're not very big. You can see this was the Sojourner and the Curiosity, Spirit and Opportunity. This was the Curiosity rover. They're not very big. They're the size of a smart car. This is the one that's on the moon right now, Perseverance, and again, not very large. That is as much mass as we can successfully land on Mars. So before we can put people on Mars, we got to do a little bit better than that. But still, they're sending back some really cool shots of Mars. And until it shed a blade, we had this little helicopter that flew successfully for almost 60 different flights on Mars. Come on, next one. There we go. Like I said, Mars is as far as we can send somebody with today's technology. And by the way, today's technology is the same technology we used in 1970 to land somebody on the moon. Same rocket system. We have better manufacturing, we have better avionics, better electronics, but the rocket propulsion technology has not changed. And until it does, the best we can get for the rest of the planets in our solar system will be the look through a satellite, an uncrewed satellite. So if one of you guys can actually learn to develop some better rocket technology, then we can send people off to the planets or the moons of those planets, which could actually be more interesting. Here is a picture of Saturn taken from a satellite. And if you were at Saturn and looked back at Earth, this arrow here pointing to this blue dot, that's what the Earth would look like if you were all the way at Saturn. And then beyond our own solar system and out into the other universe and other galaxies. And so these are pictures taken from the Hubble and the Webb telescope showing other galaxies. And nebula where new stars are being born. This is a picture taken from the James Webb telescope that covers the piece of sky that a grain of sand would cover if you held it at arm's length. So think about that tiny little grain of sand. And in this picture, each one of those points of light is not a star. Each point of light is a galaxy. I mean, wrap your brain around that number of galaxies in a grain of sand, and each one with billions of planets and the potential, or billions of stars, and the potential for billions of planets. And since you are all doing Space Day, I know I don't have to convince you here, but when people ask me, why would we even go into space? I look at a picture like this and I say, how can we not? Thank you.
Wow, that was absolutely outstanding, Marsha. Those images are breathtaking.
They're
The
cool.
fact that
Yeah.
you've been in space is just it's mind-boggling, and 5 times. So I know everybody is going to ask the same question, and we got to ask you. When I was growing up, it was my dream to go into space. It was. I actually tried multiple times, but why did you decide to become an astronaut?
So when we launched that first Mercury shot in
Mm,
1961, I was 10 years old. And we sat and we were glued to our black and white television sets as we watched this. And for the next 9 years, as we did Mercury, Gemini, and Apollo, when we landed people on the moon, I was completely captivated. And
mm,
I wanted to do that. And this was not something that really anybody aspired to do in the 60s. I mean, this is all brand new. And it was certainly not anything that girls aspired to do. And I aspired to do this.
yeah.
I looked at what those astronauts were. They were military pilots. I actually became a pilot. I started flying when I was 15,
Wow.
and got pilot's licenses. But they were military pilots, and that was not an option at the time for women in the United States. But the other thing they were was engineers, and I thought, okay, I'll go be an engineer.
That's good.
So I did.
Like you showed the Soyuz landing. That just captivates how dangerous this is. Like, how did you decide that with this unknown of launching, unknown of whether you come back, like how did you say I'm gonna do this regardless of the
Oh,
risk?
come on, I was 10. I had no fear of anything. It's a whole different thing when you ask an adult who's gone through life, what do you think about that? Well, I don't know,
Yeah,
but
that's
that I
powerful.
just wanted to do it. And going into space was, of course, the dream, but I wanted to work in space flight, in human space flight,
Mhm.
somehow supporting the program.
Was there something that you did to prepare yourself mentally for a launch?
Okay, well, and everybody will answer, everybody who's ever launched will answer that question a little bit differently. I tried to be as prepared as I could be for the work I was going to have to do when I got there.
Hmm.
And
Focused on the mission.
yeah, well, they say the astronaut's prayer on the launch pad is, please don't let me screw this up. And it's a little bit more graphic than that, but that's it. Because almost everything that you do in space has had a lot of effort and work and thousands of people that are behind it. And
I love that.
high dollar
Yeah.
value and high investment, both personal and fiscal, that went into that. And you do not want to disappoint anybody about that. And then when the time came to build the space station, the pressure was up to magnitude, because you couldn't put your piece on unless the last piece was on successfully. So if I screwed up putting my piece on, the space station was broken. And man, no pressure there.
Yeah,
So
yeah.
I sweated bullets, I'll tell you, until I got it connected.
No pressure there. But I heard as well that it was more than just about you. You really recognize there's thousands of people that could go into a mission, that could go into a launch, and they're
Oh,
all rooting for you.
thousands of
It's
them. I mean,
unbelievable.
yeah, we used to go down to the Kennedy Space Center where the guys were putting it together, and literally thank them for their touch labor, for putting their hands on it, because without them we don't fly. I mean, we're just the tip of this needle. We are slightly better, depending, than the trained monkey. I mean, because everybody else's work and blood and sweat and tears went into that particular mission. And that's true every time we fly.
Let me shift gears and then I'll shift back to something a little stronger. But what was your favorite astronaut food? I'm a big food fan. What was your favorite astronaut food, space food?
I didn't have a favorite food. All the food, so there's an interesting thing in short duration space flight, under months, but a few days, in that you get a fluid shift up into your head. And it's like when you have a cold, things don't taste right. So things don't taste right. And so
Ooh,
I had all sorts of gourmet chocolates with me and, very good stuff. And it tasted like wax. I mean, it
wow,
was that. So I didn't really have a favorite food.
that's good. I get it. That's eye-opening as well. We had a lot of students who talked about becoming an astronaut, which is great. That means the future is strong, but they question, what does it take, right? What are some tips you would give them? What are some pointers you could give them if they're interested? Is there a cheat sheet? Is there something people are looking for specifically? What would you say?
I don't know. I mean, I don't get to pick who it is, but the minimum criteria to apply as an astronaut for NASA is that you have a college degree in a science or engineering field, a STEM field. And so that's the entry criteria right there. I only have an undergraduate degree. I don't have a master's or a PhD, as most people do. But I had work experience I've been working for NASA as an engineer for 10 years before I was selected on my third application, by the way. So perseverance is another one, I would say. But science, engineering, math, physics, biology, geology, any of the ologies like that, that's important. And I always tell people, pick something that you enjoy doing, because the odds of getting selected are small. And so you ought to get educated in what makes you happy doing and supporting. And as you said earlier, there are thousands of jobs in support of space that are not necessarily the flying in space part. And there's a huge market for people to build the technology that we use in space, whether it's robotic, whether it's
Yeah,
long durational exploration kinds of things. Ultimately being able to process raw materials from a planet like Mars, in situ resource development. How do you make fuel out of carbon dioxide, or methane out of, whatever you have. And so developing those capabilities, developing rocket engine technologies, all of that is huge. The other thing that is good is experience with a team.
yeah,
Learning to work with a team, work together. Sometimes you're the leader, sometimes you're the follower, sometimes you're in control, sometimes you're doing what you were told. I mean, but working as a cohesive team. And then the third thing is handling things that don't go right.
yeah. The pressure.
I mean,
Yeah.
if you completely fold when something goes wrong, this
Mm,
is not good. But if you sit back and say, "Okay, let's go in this direction, let's try this," that kind of thing, that's the kind of attitude I think that makes somebody a good crew member.
that's really, really great. I hope you all are taking notes. These were some excellent nuggets. Like you talked about some of the technologies and capabilities that we need. What are the technologies and capabilities we need to go beyond Mars, to have, maybe even to get outside of the solar system one day and actually explore beyond, beyond our galaxy.
Yeah, the way we fly now is all, with a certain propulsion technology that expends fuel to point you in a direction and get you going at speed, and then you coast and you use the gravitational force of the thing you're pointed at to sort of help you along the way. And that orbital mechanics of slingshotting around different planets in order to accelerate yourself onto something else, that's what we're using. And well, that's great. But if I really want to go to Mars, today's technology, I can only launch at a certain time. I launch so that when I get to Mars, it will be as close as it possibly is to Earth in its orbit, which is not circular. And it takes me anywhere from 6 to 8 months to get to Mars. Well, if I had a different kind of technology, for example, say a ion engine kind of technology that can accelerate constantly at 1G, which is what we are living with here on Earth, 1G, but I can accelerate in a normal 1G for half the trip, and then I turn around and I decelerate at 1G so it feels the same. I can get there in 39 days.
Nice.
That is an engine that will only work in a vacuum. So
Yeah.
you've got two challenges. One is to get your mass out of the gravity well. You've got to get it off the planet. And we're trying to send huge amounts of mass off the planet. That technology is not changed. Then you got to get that mass huge long distances. And so the more you can accelerate it, and the closer you can approach speed of light kind of thing, the shorter the
Yeah.
duration it is to get there.
That
And
was a
then
lot
you've
of
got
good.
to then you've got the smaller technologies like protecting somebody against the radiation of deep space, of providing food and water and recycling of the air that you breathe and recycling of your liquid waste and your solid waste, you know, all of those kind of supportive technologies, all of which, by the way, have huge applications right back here on Earth.
Yes, they do. Um, it seems like I don't have as much time with you as I desire, even though I have like 40 more questions. So, one thing that you talked about is you showed those images from space and you saw those oil spills and how it changed the topography.
Yeah.
And I thought, you know, the world really looks different from space. Like, what, how was your perspective, not just on how the world looks, you know, literally, but symbolically, how was your perspective changed seeing the world from like above?
You know, I get that question a lot, and my answer is probably not what you would expect. It wasn't from seeing it from above. It was having then been given the opportunity to tell this kind of a story all over the world,
Wow.
in different places, in different cultures and
Wow.
different ethnicities and different, you know, things that aren't
Yeah.
necessarily our Western world, and learning that everybody responds to those pictures the same way. Everybody oohs and ahs at the same pictures. They ask the same kind of questions. And for me, that was the most eye-opening, to realize that people are essentially the same the world over in the
Yeah.
things that they find interesting and funny and curious and awe-inspiring. You know, they're the same. We are a planet of people. We are not a planet of diverse, you know, what you read in the news every day.
That's awesome. I'm going to wrap it up. I've learned a lot of great things from you today, Marcia. I want to highlight a few. This is Marcia's Momentum. I'm calling it Liftoff Lessons. You talked earlier, you gave us a history of NASA, and I thought everything from your past can ignite your future to lift off. That was so great to walk through. You talked about the formation flying, and it made me think, and you said it as well, teamwork is so important. You're an astronaut up in space. You got to have adaptability, versatility, and you said perseverance. You students, did you hear it? Marcia said perseverance is so important. We are the experiment. You got to be willing to try and fail. And I said, hey, the world looks different above. And you said, and there's no boundaries from space, which I love. No boundaries from space. No boundaries from space. But you talked about you can have this perspective, but it doesn't matter if you're not telling other people about it. It's about the impact. So I want to give a huge round of applause again for Marcia spending this hour with us. It has been an absolute blessing. Thank you so much on behalf of Engineering Tomorrow. I'm sure you have changed lives today. I'm sure you have ignited liftoff in other people's lives. And I'm going to hand it to Monica to talk about next steps. We hope we can have you again.
Thank you.
Thank
It
you
has
so
been a
much.
pleasure. And thank you for inviting me.
Yeah.
I have to say thank
Thank
you
you,
to
Betsy,
Milton
for
and
the
Marsh.
plug as well. Thank you for the plug,
Yes.
Betsy. Appreciate that.
Thank you to everybody from ET, all our staff engineers, and Marcia for our amazing keynote today. But thank you to these teachers who made this happen for their students today. This could not have been possible without all of your work to prepare your students and to be here for the entire event. Thank you all so much. Fantastic job, everybody. And we hope that we see you for the next one. In our chat, our ET staff has placed the links to connect you to our brand new website where you can find all of the information about our upcoming events. And we also have those exit tickets. Teachers and students, you both have exit tickets. Hope to see you for the next one. And fantastic day today, everybody. Thank you so much.